Okay, so hopefully you see things. um, I actually wanted to show, this actually showed up on, uh-oh. It always, why would it start right now? Okay. Okay, hopefully it's funny that things are going to start crashing as soon as the workshop starts. Um,
We jinxed
I
ourselves.
know,
No.
I know. Um, so one thing I wanted to show, and this literally popped up on Twitter today. So there is an R package called Data Edit R with a capital D, capital E, and a capital R. And what it allows you to do is actually when you do end up using this library, there's a function called data underscore edit. It gives you essentially a spreadsheet application within RStudio, so you can edit or create data sets within RStudio if you want to, so you don't have to jump around between multiple bits of applications. Um, I'm still very, just keep in mind that you really don't want to edit too much with your original raw data sets, because that will prevent some steps in your data analysis pipeline to be not reproducible. But if you end up getting stuck on something, this is something that you can do. It's a quick way to create like a new data column if you're manually inputting data. It's a new tool for that. So that's just something I wanted to bring up because it essentially just came out like within the last 24 hours. At least that's when I first saw it. Uh, so that's something that's pretty cool. So welcome today for part two. Let me just make sure everything's recording. Okay, and the pre-workshop survey, I guess is a little late for the pre-workshop survey since we already finished the first day, but there will be a post-workshop link that I will give everyone at the end, and that will help with just the materials that we are covering the next 2 days or these past 2 days. I already have a bunch of feedback for things I need to take out, so all of that helps. Links to useful things. So we have the slides and the materials that I'll put into the chat right now. These are links that you can go to, and they're just going to be there forever, I guess. And just as another reminder, if you are working on a single screen, the best way to, I guess, view everything is to have the Zoom window in one corner, and then your own RStudio window in another corner, and then have some space for the Zoom chat so you can interact with me and ask questions. Yesterday, we ended with doing descriptive calculations, pretty much an introduction to like how you should think about formatting your data sets and loading your data set into R, and doing very simple selecting of rows, filtering of rows, and selecting columns. And today we're going to start the process of actually cleaning and processing our data. So just as a recap, we'll take about 5 minutes to go through this problem. So open up RStudio. You're going to want to open the ds4biomed learner project. So I can show that to you a little bit. Since we opened this project yesterday, you can click this top right corner, and then you should get an option for the dropdown that's ds4biomed-learner, and that'll open up the project that we worked on yesterday. Likewise, there is a binder backup if you need the binder backup for it, and I would post that in there in the chat as well. We're going to load up two libraries. There's the tidyverse library, so we can do our basic filtering group by operations, and then the read Excel library that will allow us to open an Excel file. Once you do that, we are going to load, I wrote save, but it's load the medical data underscore tumor growth dot xlsx file. We're going to save that to a variable called tumor using the read Excel file function. And then we're going to filter the tumor data set that we have loaded such that it only contains values from day 21. And then calculate the average size for each value of group. So if you need scaffolding code, it is there on your right-hand side. And we'll take a couple of minutes to work on this. And this should serve as a small recap of what we did yesterday. And once you're ready, or if you're just ready to move on, just put a green check mark in the Zoom participant window. And then so I know roughly how many people are ready to move on. If you end up with a problem with not being able to find the data set, make sure that you're looking through the data folder. And the other thing you want to make sure is on the top right hand corner of RStudio that you're in the ds4biomed learn RStudio project, and that should help with getting the computer thinking you're all in the right location. And you should be able to navigate to the data folder in the bottom right hand corner, and you should at least see the two medical data underscore tumor growth data sets. And I am going to do a restart on Zoom because I can't actually type into the chat right now. So I will be right back. Andrea, am I showing up in Zoom twice? I think I am.
Yeah, you are.
Um,
Wonder if that's.
is my other session still sharing by any chance?
Yeah, one of you
Oh,
is
oh,
sharing.
there it is. Okay, it finally timed out.
One of your clones is sharing. Now,
Got
not
it.
anymore.
Okay. Can you reset the Zoom permissions for me? And
Yeah, there we go.
I think I fixed all my Zoom problems. I
Okay.
really hope I did.
Okay,
Okay.
good.
All right. So we are going to go through the problem. So I'm going to open up a new R script, and I have the ds4biomed project open in the top right corner, and then in the bottom here in the bottom right, I have the folder that we are working from. So that is, remember from yesterday, our working directory or our starting point. And so the first thing that the problem asked, let me believe I can I copy paste this? I can copy paste that. Is to open our project, which we did, load the tidyverse and read Excel library. So that is the library function tidyverse. Hit Control Enter to run that bit of code, and then the other function that we want to load, or the other library we want to load, is called read Excel, and that gives us the ability to read Excel files. The next step was to not save, but load the medical data set. So what we using the read Excel function. So we can say tumor gets read underscore Excel. And then in quotes, we were trying to look for the medical data tumor growth in the data folder. So that should be under data / medical data. And if you hit the tab key, it'll try to tab complete whatever you've typed so far, and it'll try to help you along the way. So we can select the read Excel, the Excel file. If we hit Control Enter there, you'll see that on the top right hand corner, we have our little tumor data set. And if we click anywhere that's not the blue arrow, you can see the data set open up in the main RStudio panel. The next question was to filter such that we're only looking at values from day 21. So remember, tumor, if we're just filtering on days equal to 21, we can use the filter function and say day is 2 equal signs to 21. And what that will do is it will take the tumor data set, look through at the day column, and if that value matches 21, it'll return that set of results for us. And you can see here, this gave us a data set that is 15 rows with 5 columns. And then the last block was calculate the average size for each value of group. So this is sort of the wording or the way you would say to yourself in your head that group by aggregate average or mean function that we ended off with yesterday. So we're going to start off with our tumor data set, and the key phrasing was for each value of group. So that is how that is like the word problem form of group by. So we can say group underscore by, and then we're looking for each value of group. So the group by variable is group. And if you have other things that you want to look for, so it's very possible that in a lot of these medical data sets, you might have some treatment group by some other demographic, and you can put a comma across every other group by variable that you want. And here the tricky part was we are looking for the average size, and sort of the way group by works is we can say summarize, and then we can say size is, or we can say average size, so avg underscore size is equal to mean of size. And now we get, and I will paste this in. Now we get, for every single value of group, we have the average size of something. The nice thing about this summarize function, and the reason why we use this outer function to just calculate the mean, is if we put a comma after this mean size, we can actually calculate other things. So we can say like min size is equal to the min of size, for example. And now you can see like you can have all of these other small summary functions, and you can create your own summary table for each value of group in this manner. And you'll see people put in a new line so people know that like, oh, you're first calculating mean, you're also calculating the minimum value. There's functions to find different quartiles, so you can get like the 25 and 75% quartile of things if you get different values. Interesting. What values did you get different? I guess like I'm trying to figure out if the first part, if you're definitely getting this group 1, 2, 3, 4, yeah, I am. Let's see. Okay. Yeah, so that's a little okay. So I sort of screwed that up a little bit. That part was a little bit unclear. So I calculated this as a totally separate question, and I think I have to change the scaffolding for my bit of code. If we had done something like this, which is probably what the scaffolding says, what you're doing is you're now looking at the average size for each group only at day 21. And that could just be me reading the question wrong on my own. Versus over here, the first time I wrote it, this was calculating the average size for all groups across the entire data set. So yes, and I think the scaffolding actually showed the filter command in there. So I guess I read my own question wrong for my own scaffolding. But yeah, so that's sort of how you can use piping to look at different subsets of your data while still doing this set of aggregation calculations as well. And if you care about like the average size across each single day, then you can say here, you can put in the day column there, and it will give you for group 1, day 0, here's the average size and minimum size across all of your patients. And then for group 1, day 1, et cetera, et cetera. So you can change and modify the grouping variable. And I will just keep this so everything is persistent. All right, so that's sort of the little recap thing that we have for today. I'm going to save this file. I'm going to simply call it 03, I'll call it recap. So it's there. And then sometime between this week and next week, I will definitely post the code by tonight, sometime within the next 24 hours. The video recordings are going to take a while, at least the one from yesterday, because I have to censor out me cursing at the screen every time Zoom crashed. So just be on the lookout for that. All right, so now we can start with the main thing that I wanted to talk about today, and that is this notion of a clean data set. So we're going to start the process of wrangling data or cleaning data, and this is one of the fundamental and core concepts of the data cleaning process. And so yesterday I talked about there are different ways or formats of data that you might find useful when you are curating your data set on your own. But there's as long as you're aware of the transformations that can happen, then you don't have to worry about putting your data set in such a format that's like inconvenient as you're entering, but only because it's useful when you're going to do the analysis. And so we're going to cover this paper by Hadley Wickham that's written in 2014. It's his tidy data paper. We'll essentially go through the first 6 sections of that paper just to show you and talk through the different components of a clean data set or a tidy data set. And so the first thing that he shows in this paper is here is a mock data set of patients and some example treatment value. And you can see here each row represents a person, and then we have a column for treatment A and a column for treatment B. He also says that if we transpose this data set such that each row becomes a treatment category and each column represents a person, the amount of information being stored and displayed is exactly the same, right? But he goes to, this is one of the points about rows and columns being pretty ambiguous terms, because we have 2 data sets that really store the same bits of information, and one is more, how do we say like one is more useful than the other? What is the terminology that we can use? And then he goes to show you another table that is this version, which we have 3 separate columns and we now have 6 rows, but the columns have a column for name, a column for treatment value, a column for result. And you can see before, if we scroll up and look at one of the other tables, it's really easy in the 2 other forms to look across a row or look down a column to see, like, to roughly eyeball, like, hey, is treatment A doing better than treatment B, or is Mary Johnson doing better than Jane Doe, et cetera, et cetera. These 2 formats allow that to happen, versus this format, you can't really eyeball and quickly filter out like how treatment A is doing compared to treatment B, right? But this is the format that your data needs to be in if you want to process your data using a computer. I just showed you the group by function before, and it's much easier now to say group by treatment, give me the average result, right? And then now you can actually do a treatment comparison between these 2 groups, right? And that allows us, and that's because we have a separate column for treatment and a separate column for result. So this all ties back into that first spreadsheet chapter about what it means to put together a good data set. And so we talk about tidy data, and so what defines each row and column. So we want each variable to be in a column. So we want a variable name for name, a separate column for treatment, and a separate column for result. Each row should represent an observation. So before we had, Jane Doe for treatment B, her result. That is one observation that you record. And then each cell is really only a single measurement, and that's really important as well. Remember yesterday, we don't want to put in, like a character for a unit in there. Maybe that's the stuff that would be stored in a column name or stored as another column, some stuff like that. And you definitely don't want a color designating different pieces of your data set. And so why do we talk about tidy data in all of these? Why so much emphasis about this process? And it's because you can use the same set of tools to essentially clean up almost every single data set. At the end, when someone looks at like a clean data set, they know what that means. Each row is an observation, each column is a separate variable, and then each cell only has one thing. So a clean data set is a well-defined thing, but a unclean or untidy data set can be messed up in so many different ways. So because we have a proper target that we know, like, hey, given this dirty data set, I can visually see or literally draw out on a piece of paper what the clean format was or is, and then you can work your way towards making your data set cleaner. And then once you have your tidy data set, then you can transform it into any other form that you need, right? So there are forms of your data presentation that might fit better on a piece of paper and show summary statistics, and that's what you use. But that all comes from like a clean data set. And so again, data sets are tidy data sets are all alike, but messy data sets are all unique in their own separate ways. And the process of taking a dirty data set and manipulating it into a clean data set, there's a couple of very common data problems that we'll go over, and this paper also goes over, and we'll show you how to use those fundamental tools to transform your data. And so in the paper, and we'll actually do this in our code as well, the first example that in Hadley's paper is this data from the Pew Research Center about a survey that they took for each religion and each income bracket, like how many people fit into that in those two categories. And you can see this is a very space efficient view of our data, right? You can fit in a lot of information on a single sheet of paper. This is pretty good if you're trying to present results at a conference or something. But you end up with the problem of, you can't ask the question of, how many people are there in each income bracket. You could, in this case, maybe like take the sum of a column, but you couldn't be able to say like for each religion, like how many people are there. You would end up like modifying your data set and taking like row sums or column sums to make that set of calculations. And so what would be a quote unquote tidy form of this data set would be this 3-column view. It'll have a lot more rows, and what we can then do is now say, how many people do we have across each religion? And then we can now say group by religion, sum the frequency, right? Or we can say group by income, sum the frequency there. And then we can get different calculations based off of our data. And so this transformation is going from a wide data set to a long data set. And if you sort of look at this page for like a little bit, you'll notice that in the wide data set, each value of x, the x gets repeated, and then that value gets replicated for the value there. So this transformation, or this pivoting of tables, is a very common data transformation step. And once you see a lot of these data sets that get presented, hopefully by the end of today, you're able to identify like, oh, if I want to actually process this data for my own work, I would need to do this particular step to it. And so another visualization that we have that you can see is like this GIF format that is all of the information is still there. One is essentially the inverse of the other, although there are exceptions to that. But all you're doing is transforming how the data is presented. One that is more space conscious and can fit on the screen better. The other is essentially what the computer will need to run these calculations. So that's the first problem we're going to address. Is what happens when our column names, what happens when a variable is stored in a column. So we're going to open up a new script. I'm going to hit the session key and then hit restart R. So we're starting over from a brand new session. And we're going to load up the tidyverse set of libraries. And so the first thing I'm going to do is we're going to load up a different view of our tumor data set that we've been working with. So we're going to say tumor gets read underscore CSV. It's going to be in the data folder. And you should have a data set called tumor growth underscore log. And if we look at this data set, or if we click on this data set here, we have the same exact tumor data set as before, except now it's currently in wide format and we want to turn it into long format. And so here, this is a view of the data that would be useful if you're manually inputting data for each patient, right? So each row in this case represents a group and a patient ID, and then you have the days from 0 to 28, and you can fill out the numbers across each row, right? So this is a view of the data that's really useful if you're sort of like on the floor and this is your patient for today and you just need to log in their set of values. You can very quickly look across the data set to see how tumor growth is changing over time, stuff like that, right? And so this is, again, a view of data that is useful for certain applications, but it's not useful in the sense that we can't say, group by, for each group, and each patient give me the average tumor size like from these set of dates or something. And that problem that we had from our recap question, we can't answer that question in the data set that it's currently in. Just as another aside, the data sets here, if you want a place in R to, my Zoom chat, okay, has officially crashed. Okay, so there is a data set here, and I'll put it in my notes so I can paste it towards the end and send it to everyone. But there is a GitHub repository. Essentially, there is an R package called medical data. You have to do a few other things to install it. It's not as straightforward as clicking the install button, but this is an R package that has a lot of these medical data sets that you can tinker with if that's what you want. And they're all coming from actual studies, and I will figure out a way to paste that in. So we have our tumor data set, and you can see if we run that variable, we get the output on our computer down here. And so the thing that we want to do, or the problem that we have right now, is each one of our days is its own separate column, right? So this is one of those like symptoms of your data set that if you see like 0, 1, 2, 3, 4, 5, 6, and it's like, what is that representing? Oh, that represents the day in the study. That is that should be a trigger for you to say like, oh, these columns need to be in its own separate single column, right? So the days here, which are usually variables, a single variable is right now totally separate columns. And so how do we go about fixing this? There is a function called pivot longer. So we can say tumor. We're going to pipe this function into a function called, we're going to pipe the tumor variable, or our data set, into a function called pivot longer. So we're going from a wide data set that has many columns to a long data set with many rows, so it becomes longer. And the way we use this function is we need to specify the columns that we want to pivot into its long form. And so I showed you yesterday, just like using the select function, you can manually input or specify the columns that you want to select. But it gets tedious to say like 1, 2, all the way up to like 28. Like maybe you're okay typing up to 28, but sometimes these column names can be like 1 to 500, and that's not feasible for you to actually type into your data set. or into this function. Another thing you'll notice that during the printout of our columns, there's this backtick in front of our column names. So this backtick is usually the key to the left of the number 1. It's probably a key that you do not enter. And so to specify the 0 column name, and that's part of it is because R does not really like column names starting with a number, so it has to sort of put a quote around it. So we're going to start from the 0 column, and then within the tidyverse there is this special notation that allows us to select everything from 0 all the way to the end, right? So we're selecting all of our columns from 0 all the way to the last column in our data set. And so one way that the tidyverse allows us to select multiple columns is using a colon. And then we can either type in 28 here that says select all the columns from 0 to column 28, or we can say there's another built-in function called last underscore col, and this will give you the last column in your data set. And doing something like this is a little bit more useful because let's say all of a sudden some of these days go up to 31, you're not hard coding one of these numbers into your code. And so if we run this little bit of code, you see that we essentially get our original data set back. We have our data back in long format. So we have a group, an ID, the day, and then the value for that particular tumor reading. By default, it created, when it pivoted those columns, by default, it created 2 column names for us, one called name and one called value. And so we can overwrite those column names or default names after the selection. We can say names underscore 2, and then we can say day. And then we can also say values underscore 2 is equal to size. And now if we run that part of our data set, we get our long form of our data. And then we also have our 2 proper column names, one called day and size. And if we want, because this is now a processed data set, we can save this into a new variable called tumor underscore tidy. And so now we have on our right-hand side this tumor tidy data set that is essentially the same thing as our original data set. There's a few more rows because you'll see that this NA, not every single day has a value, and so during the pivoting process, it's also retaining this NA value from the original data set. And so now we can actually go and start the process of asking a question of, like, for each group and day, what is the average size for our patients, right? But there's a few more things that we want to be able to do. If we look at just our data set, and if we run it, part of the tidyverse, when we use the tidyverse set of functions to load in a data set, at the bottom here, you'll see it tells us the number of rows and columns. It'll give us the column names that we have in our function. And then right underneath, it gives us the data type that column is being stored as. And so we have, DBL stands for double, which is the computer science way of specifying a floating point number or a number with a decimal in it. There's CHR for character, so that's because it's not really a number. We have another double that represents the person ID, another double that represents the size of the tumor, but the day of the week right now is currently marked as a character variable. And so we want to be able to turn this day column into a numeric column. And so how do we go about doing this? Within the tidyverse, there is a function called mutate. Mutate is a function that modifies or mutates another column. And so the column that we want to mutate, or you can use mutate to create a new column, or you can use mutate as a function to overwrite an existing column. And so I'll show you this in two ways. We can say day underscore num. We're going to create a new column called day underscore num, and it's going to take the day column here and turn it into the numeric representation instead of the character representation. So in R, there's another function called as.numeric, and it will do exactly what that says. It will take whatever you give it and turn it into a numeric representation of it. The thing that we want to pass as.numeric is day. And so it's going to take the original day column, turn everything into a numeric variable, and assign a new column called day underscore num. And now if we run it, you'll see that we have a new column called day underscore num. It is now a double, and it's the numeric representation of our original day. So now that we have this, we can then go about and go back to our original problems that I ended off with yesterday. We can then say group by the group by the day underscore num. And then so for each group and each day, we can then say, give me the average size. Right. So in this case, we have another issue in our data set. And remember from before, our data set had a bunch of missing values in it. And one of the things with the mean function, so if you put your cursor before the opening bracket of mean, if you hit the F1 key, it will open up the help function on the right-hand side. And so one other question I got during the chat was sometimes because R really doesn't like having column names start with a number, it'll put a character in front of your numbered columns. I guess I'll show you how to do it during the next break. You either keep it because it really does not like having numbers beginning with column names beginning with numbers. There's another thing during the pivoting process. In the next step, I'll show you how you can cut off the little x that might be loaded up. So in mean, if we look at the mean function, there is a parameter called na.rm. And so one of the problems that comes up with the mean function is that if I tell you to find the mean of 1, 3, and 5, R will give you the mean, which is 3. But if I tell you to give me the mean of 1, 3, 5, NA, or missing, so that's 4 numbers, R, when the mean function sees that sequence of numbers, it's going to return you back NA. And it's because that there's an NA value in that sequence you're trying to calculate the mean. It doesn't know what to do with it, so you have to tell it, hey, if you encounter an NA value, I want you to drop that observation. And so within the mean function, we can say na.rm, because that's the parameter that this function takes. And we can say remove the na value and set it to true. And that is in TRUE all caps. And what that will do, what it doesn't do is replace the na with a 0, because then that's actually will affect the arithmetic mean. What it's doing is if I give you 1, 3, 5 na, it will only calculate 1, 3, and 5 and give you 3. So it's going to drop the na value from the numerator and the denominator as it's doing the calculation. And so now we can say, now we can do our group by calculation. We've done some data processing of turning a character string into a numeric string, and now if we can drop missing variables or missing values in our mean function. All right, so the next problem that we'll cover, and I'll talk about this before we go on our first break, is this notion that multiple variables can be stored in one column. This is an example from the paper that is for each country and each year, the tuberculosis counts for gender and age group. So M014 stands for males 0 to 14. M5564 stands for males 55 to 64. And then we have 65 and up, or unknown. And then we have the same set of columns for female. And this is somewhat similar to the problem if R loads in like an X in front, we'll end up processing off that first letter. So this becomes a problem because if I look at this 52, what does that 52 represent? Well, it represents for given country and year, but if I look at the column, that 52 represents a gender count as well as a age group count. And this is a data set, again, that's really space efficient. You can have two of these tables, one above each other, and essentially show your entire data set. But you can't actually go and ask the question, how many total males in the year 2000 had tuberculosis across the world? You can't answer that question in the data set in the format that it's in right now, at least not easily. And you can't really say for each country, give me the total number of tuberculosis counts for 65 and above for males and females. That becomes a problem that gets more and more difficult. So if you think back on, how would I do a group by operation, or how would I calculate those means? Those are if it becomes difficult because you can't specify a single column, those are little symptoms of your data set needs to get processed in some way. And so usually when I get a brand new data set, I will actually get out a sheet of paper. I will sketch out, here's my starting data set, and then I will sketch out the views of the data set here, which is this is what I want my final data set to be. I want a column called country, I want a column called year, a column called sex, a column called age, and a column called cases. That is the final data set that we want. And so in this current example, if I go back again, you see the same problem that I just covered, which is these column names should be in its own single set of columns, right? So at least we know the first step, one step closer to our final result, would be some kind of pivot longer operation. And so if we do that, we get this version on the left, which is we'll get a column that has M014, M1524, but we have the case counts. And that's one step closer to our final result. And even if you don't know any programming whatsoever, or data processing, and I say like, hey, I have this column that says like M2534, and this column represents two variables. The M stands for the gender, and then the rest of the thing stands for the age group. How would I go about splitting this column? And without knowing any programming, you might say like, oh, if all you do is make a cut down the first character, you'll be able to do a split that will eventually turn your data set into the one on the right. And so that's the process that we'll almost do. We won't actually put the 0-14, but we'll be able to split our data set into something in tidy form. And so we'll take a 5-minute break, which will put us at 2 past the hour. And so take a break, and then we'll go on and showing how we can write the R code to do this type of data transformation.
Dan, are there two of you again, or I want to make sure I don't take away host? I think there's only one.
I think the other one will eventually time out, and it should be
Okay.
fine.
Because one of you is not co-host, but I don't know if I should do that because I think it's your other one. We'll see if it goes away.
Yeah, it happens every time I move the little Zoom panel thing like out of the way. So I'm just not going to touch that anymore.
Well, that's you speaking. I better let me make that one co-host.
Oh, okay, cool.
Can you chat, or is your chat gone?
My chat works. So I could see chat before. I just couldn't like click on anything Zoom related. Like it was totally frozen, which is weird. That's a new problem.
Yeah. All right, good. I chatted that link too. That's really helpful. The one from Higgy.
Yeah, Peter. And I have towards the end, there's like a whole bunch of resources that we'll go over. And Peter's part of it too. So, okay. So we're going to go through that example, the tuberculosis example. Give me 1 second. There's okay, so we'll go over the tuberculosis example that I just showed in the slides. And so we'll say TB, which is our TB data set. We're going to read underscore CSV. And we're going to load up the TB data set, which is under data / and it's going to be called TB underscore long. And this is the data set that's going to say turn it into the long form example. So it's not in long form, but we'll use this as our long form example. So you can see here, if we look at TB, this is the exact data set that we had from the paper. We have our columns, and it has the same problem. Each value or each count represents a gender as well as an age group. So the first thing that we did is we want to identify, hey, these column names they shouldn't be separate columns. They should be somewhere where there is a column that contains both of those bits of information. And so that is the sort of the thing that you want to identify in your head and recognize that, oh, this is a pivot longer operation that we want to conduct. So we can say TB, then pivot longer. And so this is exactly the same problem we had before, and the code is going to be the same. So remember, the way we use pivot longer is we want to specify all of the columns that we want to do this pivot operation in. And so we can say M014 all the way to female unknown, right? We can say from here all the way to last call if we want. But I want to show you another way because this ends up being pretty useful if you work with survey data. Because all of the columns that we're currently interested in begins with the letter M or the letter F, right? So the other columns, country and year, don't start with that letter. There's another quick way we can do these quick selections with, and we can say starts underscore with. And that ends up being its own little function. And we can say, hey, I want you to select all of the columns that start with M or F, right? And so because there's two things that we want to specify, we can't simply say M, F. we need to pass starts with one object or one thing, even though that one thing contains multiple values. So we have to essentially create almost like a list of values that we pass into the starts with function. And so the way we do that in R is we create we concatenate or stick together a sequence or a vector of characters or values. And the way we do that is using this C function. And so now we can specify starts with M, starts with F. And so using the C function, it allows us to create a small group of characters that we can specify. And if we run this, it will find all of the columns, just like before where we said start from 0, go to last call. Now we're saying, hey, pick all of the columns that starts with M or F. And now we get this long view of our data, which has 3,200 rows and 4 columns. And that is the second or the first step in the data cleaning process. So we can save this, or we can pipe it into another variable. So the next thing is we want to do this split across this first character, right? So let's save this into a variable called tb_long. We can save our intermediate variable here. And so we now have tb_long, which is that intermediate state. And the next thing that we want to do is split off the M for the gender with the rest of the characters, which represents the age group. And the function that we do to do that with is there's a function called separate. And separate does what it roughly sounds like it does. You give it a column, in our case, the name column, and then you tell it how you want to split this column into. So we want to split this column name into 2 separate columns. So we can say into equals, and then we have to provide the C function again. We want to split this into a column called sex and a column called age_group. How do we want to separate this? There is a parameter in here called SEP. And what this allows us to do is we can either give it a number, for example, 1, and it'll say, oh, I'll just split based off of the first character. If you have a comma separated value in here, for example, sometimes you have a column that represents like a bunch of tags, you can separate that by passing in the character string, the comma. But here, because we want to just split off of the first character, we can say sep equals 1. And what that will do is it will break that original name column based off of the first character. The first value will be turned into a new column called sex, and that value gets inserted there. The rest of the character in that name column gets turned into the column for age group. And then now we have our new tidy tidy data set where we have country, year, sex, age group, and value. And then we can go back and do that whole, you'll notice that we can now do something like group by sex, give us the count across all of the years, for example. And then don't forget, because we might have missing values in here, we also have to provide this na.rm if we're doing this mean calculation. Okay, the last form of data sets that data problems is a combination of the two things I showed you, which is variables being stored in both rows and columns. And this is one of those problems that you don't necessarily see right away. It's only during the cleaning process do you recognize like, oh wait, there's actually more things wrong with this data set than I initially expected. So given this data set, this is a data set for a given ID, year, month, temperature, reading, and day. We have a reading in, I believe this is in Fahrenheit. I think so. It doesn't really matter in this example. But if we go back to the previous examples, one of the things that you'll notice right away is we have day 1, day 2, day 3, day 4, et cetera, et cetera, et cetera, et cetera. That set of columns, and that should trigger in your head. This is probably fine for data input or for whatever way that the data was submitted and stored, but if I need to do actual work with this data set, I might need to transform or pivot longer into another format. And so if that's the first thing that you see in this data set problem, we'll do that. So a lot of data processing actually is this turning it into long format. So we'll do that part first. So at the end of the day, like literally take out a piece of paper and say like, what do you want in your data set? Well, if I look at this value here, this 27.3, that is a temperature max reading for day 2. So I might want something that says ID, year, month, element, day, value, right? And so draw it out on a piece of paper, so just so you don't get too overwhelmed with, I'm trying to program, but I also need to also keep in my head, like, what is the clean form of the data set I'm trying to work with? I do this all the time when data sets get complicated, or when I'm talking to someone, just so everyone's clear what the final data set needs to look like. Draw it out and sketch it out on a piece of paper. It becomes really helpful. So the first thing that we know we want to do is do this pivot longer operation. And so we'll get this value on the left, which is very similar to the tuberculosis data set that we had before. And so now we have ID, date, element, and then a value. But remember that the last form of the tidy data like principles or the rules was like each observation really should represent like one reading, like one observation. Like each row should represent one observation. And the problem with this data set on the left is if you ever encounter a data set where a bunch of things are repeated except for like one set of measurements, this is one of those hints that you want to do this other pivoting step, right? So ideally, one observation, the observational unit that you have is the day or the date. And so you're trying to measure the maximum temperature and minimum temperature for each day. Not instead of having a separate row for max and a separate row for min, right? And so if you ever encounter a data set where like, hey, a bunch of these like ID like variables are repeated, and then the only thing changing is like this value thing here, again, that is like a sort of a small hint that you might want to pivot in the opposite direction. And so this transformation here takes a single column and pivots it into its wider format. So in Excel, this is like literally the pivot table function. And we can then specify a separate column for Tmax, a separate column for Tmin, and then the value that's represented that's tied to each of those readings. So we will go through this example, a very similar example in our code. I have put together some data from CMS, and we can say read CSV. There is, under the data folder, there is CMS utilization. And this is a data set that for each state, FIPS code, variable, gender, some category, how much of the this is a data set of CMS utilization for rates by state, demographics, year, and some other measurement. So one of the other measurement is like the utilization per capita spending, or ED visits per 1,000 beneficiaries, et cetera, et cetera. And you can see here towards the right-hand side, we end up in a scenario where each row has all of its separate years together as separate columns. And so that's one thing that we might want to recognize, that like, hey, this is useful for, if you're trying to look up something in an Excel table, but it becomes harder for some other data analysis process, right? And so we might want to pivot this into a longer format if we want to end up asking some kind of summary statistics question. And so we'll do that step first. That this part is something that we've been doing. This is our third time doing this step now. Is we will run pivot longer. Pivot underscore longer. And we want to specify all of the columns from 2007 all the way to 2017. And so there's many ways that we can do this. I can right now pick backtick 2007, close backtick, colon, and then last underscore call. And then, just like our first pivot longer example, I can pass in the parameter for names underscore 2 equal to year. And then that way, when we do this pivot operation, instead of the default value for name, it is now this new column name called year. And it just makes, if we're in the process of cleaning our data set, we might as well make our column name sort of meaningful along the way. We can then save this intermediate into a variable. So we can say CMS underscore long gets this set of values. So now we have this totally separate CMS long data set. And the problem, or one of the things that I've noticed in this data set, is we have, per capita spending for the year 2007 and its value. And if we scroll down a little bit more, we have per capita spending standardized, and then we have ED visits per 1,000 beneficiaries, and then we have hospital readmissions rate percentage, et cetera, et cetera. And everything else in this column, minus this variable column and then this value column, is repeated multiple times across each row, right? So that is one of the hints for like, hey, something else is kind of going weird with this data set. Because it would be nice to have, for each state, FIPS code, demographics info, year, we just have a column that says per capita spending annual, and then the value underneath, and then the standardized value underneath, and then the beneficiaries per 1,000 underneath, and the hospital readmissions rate underneath, et cetera, et cetera. Like, so each row becomes a single observation for a particular state and year, along with the other demographics. And so we talked about pivot longer this entire time. Now we get to use this other function called pivot wider. So this is our original data set that we have here. And we want to now use the pivot wider function. This function takes two inputs. The first thing we want to say is, what is the column give me one second. What is the column that for each unique value in that column that will now become its own separate column? That is, we want a separate column that said per capita standardized, hospitalization rates, et cetera, et cetera. So what is that column? And so in our current data set, that column is called variable, which is sort of useful. So there we say names from variable. So the names in this column, this is where it's pulling the new column names from. And so that goes into a parameter called names from. And when it does that pivoting, what column does it use to fill in the body of the table? And so that goes into a parameter called values from. And then we specified this last column here, which is like that spending, that dollar amount. And that column is called value. So we can run that bit of code. It did an error. And then we can take that and then we can say CMS underscore tidy gets that data set. We can look at this data set. And now if we look across for Alabama, states FIPS, a couple of demographic information, we now have per capita spending, standardized ED visits per 1,000 beneficiaries, and hospital readmissions percentage all in a single row. And that becomes much easier to say, like, what is the average hospital readmissions percentage for all of our years? Like group by year, average that column, right? So now we can actually do that versus before, all of this information was all stored together in a single column. Maybe you wanted it that way, so you can pivot it longer and say group by that variable column and then calculate average value. That's something that you can do as well. And that's all possible because we're able to understand how to transform our data from one form to another for the actual calculation that we need. Okay, do I have any questions along that? I'm going to save this file right now, just so I don't lose it. I'm going to call it 04-tidy. One of the questions I got in chat was sometimes when you load up data into R, for one reason or another, it was... Let me see if I can replicate the result and then... Yeah, okay. So sometimes, depending on the function that you get into R, because R really does not like column names that begin with numbers, it will sometimes force put a character, usually the letter X, in front of your column name. There's a few ways you can deal with this. If you know that in our current example, if you know that these columns that all begin with the number is something that you're going to pivot, I would do that pivoting step first and then deal with removing this X character. There is a way to remove or deal with column names. I don't know the most efficient way off the top of my head. I can look it up during the next break, but I'll show you how you might be able to work with this X character after you do your pivoting step, right? So this is sometimes so we have our tumor data set. I said usually we say tumor. We're going to go through the same example again. So it's pivot longer. We're going to start from x0 all the way to last underscore call. And that should give us this column just like before, with this X with this name column in there. And the way you can deal with that, one way you can deal with it is using the mutate function, which is one way to change a column. So we can say mutate, we're going to say this is day is equal to, and within tidyverse, there should be a set of functions that begin with str underscore. And you can say string replace, and we can replace all the values in name in the name column. We want to replace the letter capital X with an empty character. And so that's one way you can go about removing or doing all of these weird or special string manipulation or character manipulation functions that might pop up. I don't know the most efficient way to do it to modify column names without writing way more code off the top of my head. But hopefully that ended up helping. If not, just let me know. So if you ended up getting an error called object name not found, make sure that hopefully you did this.
Are you muted, Dan?
Yes. So if that's actually funny because the captions will go on, but
I know, that's how I can tell. I'm like, is he speaking? Yes, I can read it, just can't hear it. That's kind of cool.
So yeah, if you're having issues with this little bit of code, I guess I can paste it to everyone. It uses read.csv, which is the base R version of reading in CSV files instead of the tidyverse way of reading CSV files. So things will look a little bit differently, but hopefully that little snippet of code is able to reproduce all of the potential problems. Mainly the issue is I sort of took a shortcut, and instead of typing in like the new column names, I just left it as the default name and value. So if you end up with a weird like name not found or this column doesn't exist, it's probably because the step before didn't have this column called name. So hopefully that dealt with all the issues around there. Just let me know if in chat if you have more questions around that. We can bounce back. Yeah, so that is the so the illustrations of all of these tiny little monsters come from Allison Horst. They wrote this blog post called Tidy Data for Reproducibility, Efficiency, and Collaboration. So that's where these figures are all coming from. And so the main point for this block was really to show you like, hey, these are really common data transformations, and they play a role into every single following subsequent step in your data analysis pipeline. I showed you those group by calculations yesterday because if you can think about one way you can think about whether or not your data set is clean or tidy is if you can do that like for every value of this, give me the average value of that. If you ask yourself that question, and if you can't actually point to the columns to make it happen, then you probably need to think about something in this tidy data process to help you get your data set in a way where you can point to the columns to make that calculation. And that same thinking applies to when you start plotting, which I'll show you a very quick intro next. Plotting plays a role into this. Fitting models also play a role into this. So I will very quickly go over how you can plot, how you can fit a model, and then hopefully this ties into the rest of the UVA stuff for this week. So yeah, any questions around there? We can take a short break. So let's take a 5-minute break, and then we'll round off the rest of the class with an intro to plotting and an intro to fitting logistic regression models. One question I got was, when do we use like the double quote or the single quote? Sometimes I'm really bad about being consistent with it. I try to use double quotes all the time. It doesn't matter most of the time. So for example, all the points where I wrote double quote, you could have replaced it with a pair of single quotes and it's exactly the same. The reason why I sometimes don't use single quotes is it's more common in English text to have a single quote in an actual word, like apostrophe S in names, or if you have large strings, like apostrophes are more common, in which case like you can't begin the text with a single quote because it'll cut off at that part in the string or the word that you're looking at. So I sometimes use double quotes if I know there's a single quote somewhere in the middle. If I know there's a double quote in the middle, then I'll use single quotes on the outside. So the other question is, when do we use the backtick, which is the key to the left of the number 1? For the most part, you almost never use them. In R, and if you loaded up your data in Tidyverse, it will tell you when you can use the backtick. If you have column names that have a space in it, that is one place where you would have to put backticks around the entire column name. So you saw here, every time I refer to a, well, maybe not here. So remember, let me load up this stuff from yesterday. Remember yesterday when I talked about using select to pick on group, day, and size? If your column name had like size, space, like for example, this is one location where you have to put a backtick, because otherwise it's going to see the space as like some other character, and for the most part computers really don't like spaces, so you have to specify like, no, I actually mean this whole thing as one item. So that's one other location where you'll see a backtick. The other location you saw today where you saw a backtick was if the column name began with a number. For the most part, computers will interpret things that begin with a number like as a number. So if a column begins with a number and it doesn't automatically append the X in front of it, then you would have to use a backtick to point out like, no, I mean the column name called 2007, not like the number 2007. The other question is when to use read_CSV or read.csv. So all of the Tidyverse is essentially maintained by the folks at RStudio, and they try to make things super consistent within themselves, and they maintain like a parallel set of packages. Read_CSV, if you look up, if you compare like this tumor, I'll call this tumor base. For the actual question is, use the one that actually worked. If read.csv worked, then do whatever you want with read.csv. Some of the defaults might be different. As long as you're in version R4.0, most of the parameters of how things get read in using read.csv is going to be the same as read_csv. If you use read.csv, you'll notice that if I print it out, it doesn't give me that like somewhat prettier output. It's going to give me like the first like 2,000 rows of output, and it's just going to dump it all on the screen. And you'll see that underneath each of the columns, it doesn't give me the data type, and if a column begins with a number, it will prepend an X in front of it. So that's something that read.csv will do. Versus read_csv, you'll see that it'll give you like whatever corner of your data set fits on the screen. It'll color things nicely. Technically, there's a difference in the actual object that got loaded. Read_csv will create a tibble, which is the RStudio's like enhanced data frame object, versus read.csv, which is the base R function, will give you the base R data frame object without any of the bells and whistles that come with it. So those are small differences. And this goes more into our internals. There are small differences between working with a base R data frame and also a tibble. So there are small differences there. For the most part, those differences only come up when you are trying to write larger like functions with these objects. There might also be character encoding differences that I'm not totally sure. So sometimes, you know, it might like read.csv might have read your data set using like Latin 8 encoding versus read_csv read it in as UTF-8, and then, you know, your data set, your original data set like had some weird character that it couldn't convert properly or for some reason or another. That is also a possibility of why things may or may not have worked. At the end of the day, it's really hard to tell you like why something worked or why something didn't work. I guess that's like my main point. Hard to tell without actually like going through it with you, like step by step. Okay. So for the next, very quickly, I'm going to go through what the major components are of plotting using ggplot2 is like in R. And so the most important thing when we start thinking about what can we do with our data set is we have to understand like what type of information is stored in each column, right? If it's a number and it's continuous, then we have a continuous number like the size of our tumor in our tumor data set example. But then we have nominal data sets, so that could be something like our treatment group. One treatment group isn't better than the other treatment group, they're just different groups. And so we have, 1, 2, 3, 4 doesn't really have an order to it, so it's nominal. Then we have ordinal groups. Typically you'll see those in like Likert scales or Likert scales. And there is an actual sequence, like 1 is less than 2 is less than 3, etc., etc. And then another thing that's really common, especially if you're working with like these medical data sets, is binary variables, which is a subset of ordinal variables. And typically this is the variable that's like yes or no, the person got cancer, yes or no, the person got sick, given this treatment, like yes or no, this person hit some kind of point that we were interested in seeing, right? So you'll see a lot of medical problems. Usually the first thing they end up doing is trying to find like a binary outcome for something, and that makes it such that like the analysis that we do ends up being like a logistic regression. So that's how those two things sort of tie together. There is a very long two long workshops by Thomas Lynn Peterson, who is the current maintainer of ggplot2 at our studio. And this is a graphic that I took from his workshop. ggplot runs in this layering system. And so the first layer we specify is what is the data set that you want to plot. Then on top of that, we give it a mapping layer. And the mapping layer essentially says, given the data set that you just provided, what columns do you want me to use for the X and the Y? It doesn't mention anything about what you want to plot there. All it's saying that like, oh, if I'm going to make something, I'm going to look here to figure out what my X points, my X coordinate is. I'm going to look here for my Y coordinate. On top of that, there is like a statistics layer. So if you're running a bar plot, you're typically, you have counts of something. So the statistics that's being run is like a count or a sum, stuff like that. Usually you don't need to specify statistics and scales, and you go up into the geometry layer. And that geometry layer is the actual shape that's going to be plotted in your ggplot. So if that is a scatter point, then your geometry is a point. If it's a bar plot, then your geometry is a bar plot. Box plots are a box plots geometry. And a lot of those geometries come with a default set of scales and statistics with it. And then on top of that, just like the group by operation allows you to make a separate calculation for each variable, you can actually make a separate plot for another variable. So you can look at group dynamics just by specifying like which variable you want to split your plot out into. And then there's coordinates, like you can specify a map coordinate system, or typically we're in regular Euclidean XY. And then if you're at UVA, maybe the folks in your lab or UVA has their own ggplot2 theme. You can literally take the default theme and then someone else can specify a color scheme, and then you can say add on this other color scheme so you don't have to manually tweak every single thing. And so these are the components of a ggplot figure. And then right now we will create a new R script. I'm going to save this right away and just call this 05 viz. And I'm going to run session restart R just so we have everything restarted. Okay, let's see. The first thing we're going to do is we're going to say library tidy first. Then we're going to load up the ggplot2 dataset, ggplot2 dataset, library, sorry. If you don't have the medical data library on your computer right now, so if you say library medical data, which is Peter Higgins's medical data package, what you can do to install it on your computer, and this should be relatively quick, is if you run this command, shoot, my chat is broken.
Oh, typer, but hold on. Oh, I just lost your screen now. Oh, you got it. Yay.
Okay, so if you run that command in your R console at the bottom, it should install the medical data R package for you. And this is the command that you would use to, not every single R package is on cran, which is what gives you the little install.packages command. So if you ever see like a package that's hosted on GitHub, all you need is their GitHub username and then the name of the project repository. So this is coming from Higgy 13425 / megal-data. If you put that in, install_GitHub. Ooh, there's no package called remotes. Okay, we can install remotes. So to install remotes, you can say install.packages remotes, and then from remotes, you can install GitHub from there. I thought remotes was pre-packaged with tidyverse, so that is. And these installations should be pretty quick, so give me a green check mark when you at least are ready to move on, and put a red X when like something is horribly wrong and you definitely don't want me moving on. Hello. Hopefully my audio is working.
Yeah, and I just made you co-host again.
Yeah,
hopefully.
it really doesn't like me typing things in chat today.
Oh, weird.
It was fine right before until it hit 3 o'clock, 2 o'clock. So hopefully those two commands should get you with the medical data set on your computer, because we're going to use the package in this next example. All right, so we should have these three packages all loaded up. A lot of times these are packages, part of the package, because people want to show you how this package works, will come with a lot of built-in data sets or pre-packaged data sets in it. This is a special package because this is a package that has nothing but data sets in it, which is great, but you can do that as well. So what we're going to do is there is a data set called blood storage in our medical data package, and instead of typing blood_storage every single time, I'm going to reassign it to a variable called blood, just so it's a little bit less typing. So this is and I'll read this off of the actual dataset description. This is a retrospective cohort study of 316 men who have undergone radical prostatectomy and received transfusion within 30 days of the surgical procedure and had available PSA follow-up data. And the outcome of interest was time to biochemical cancer reoccurrence. So that is part of the data set that we're looking at. You'll notice that if I look at the blood data, it doesn't come up in that little tibble format, and that's because the way this data set was stored was as a regular base R data frame object versus the somewhat prettier way of the tibble object when we have been loading things and using things within tidyverse. So one of the things that we want to do when we're looking at our data set is first we want to get a sense of all of the column names that we have to deal with. If we look at the top right hand side, there's 20 variables. We can click on it and then scroll over to see all 20 column names, but there is a function that gives that to us right away, and that is called names. And if we give names the object blood, which is our data set, all it will do is give us the column names in our current data set. So this is really good to make sure that everything that you expected to be loaded is there, like the first row in your data set was loaded properly. If you're looking for a particular if you're looking for something that says like, oh, age doesn't exist, and then you run names of your data set, you'll notice that like, oh, okay, age starts with a capital A. Or sometimes because of how people process their data in the center, try to center things, it might be space, space, age, space, space, right? Like you might have weird spacing issues in your column name. So that is something that you might need to be mindful of, and the way you can figure that out is using names of your data set. So given this particular data set and what I told you, which was the outcome of interest was time to biochemical cancer reoccurrence. So that is something that we want to be mindful of, and that is a variable that we care about. There was also a reading of pre-op PSA. That is something that we care about. And so these things fall into different categories of nominal, ordinal, binary, continuous, or discrete variables. So the thing that we care about is this reoccurrence variable. And so when we are going through exploring our data, we want to keep in mind what are the columns that we care about. So for us right now, given our blood data set, we can say group by recurrence. So for each unique value of recurrence, and in our case it's just 0 and 1, we want to summarize, and instead of getting the mean of how many observations are there, all we care about is like how many rows of data there are. So we can say count equals n, which is n as a function, and what it will do is if we run this, for recurrence values of 0, which means no recurrence, there are 262 observations or rows in our data that have that. And then for 1, or recurrence value of 1, there are 54 rows in our data for that. You have to be careful when using n because it's counting actual rows of data. So if you have a bunch of data that is all NA and missing, or has some other placeholder like 88 or 99 are pretty common in medical data sets, it's going to count that as well. So if you end up in a scenario where like you're running n and all of the counts are the same, you might have to think about how you're actually tabulating your data set. So this is essentially what we've done is manually create a frequency count. But we can use this as a way to introduce us how ggplot works in our data set. So remember, and I'll go back to our slide here, ggplot is based off of a layering system. We first specify our data, then which columns map to which axis in our data, and then we can go to which type of plot we're trying to make, which is the geometry layer. So let's build up our ggplot thing one at a time. So we can say ggplot. We first specify our data, so data is going to be our blood data set. And if we run it, you'll notice that in our studio, the plots panel will open up, and all it gives you is a empty square gray box. And that's because what we have did was, all we did was put in a data layer. We haven't told it to do anything with it yet. So remember, the next thing we have to specify is a mapping. So if we hit comma after blood, and if you hit tab, RStudio should help you with like what other things go into the ggplot function. One of those things is the mapping. The mapping gets a little weird. The notation is weird because it's mapping is equal to like another function called AES for aesthetic. This is sort of part of the reason it plays into how ggplot works internally, but this is sort of like the notation that ggplot works on. So within the aesthetic mapping, this is where we say, hey, for the X column, or on the X side, we care about recurrence. So that's the variable that we care about. And you'll notice if you run that little bit of code, we haven't really made any, there hasn't, like, nothing's been drawn yet on the screen. The only thing that has happened is on the bottom, we get this recurrence and then some kind of set of numbers because recurrence only has values of 0 and 1. So now what we want to do is there's a plus, so we're actually using plus. Instead of this greater percent, ggplot uses the plus operator. And this is because ggplot happened before this percent thing became popular. So now we're literally going to add in the geometry layer. So the way we add in the geometry layer, we literally put a plus, then we say geom underscore, and then all of the geometries begin with geom underscore. So once you have loaded in ggplot and you type in geom underscore, RStudio should pop up with all of the available geometry objects that you can plot with. So you can make a blocks plot, you can make a density plot, you can add histograms, error bars, etc. The one that we're interested in is bar. So what it did was it created a bar graph of our recurrence column, and bar graphs by default gives us a frequency count. And this essentially mimics the 0 has 262 and 1 has 54, and that is ggplot's way of doing that count for us. Okay, I'm going to move ahead a little bit for time. So all of the other columns that we might be interested in, we also want to get a sense of what things look like using ggplot. So we can say ggplot data is equal to blood. Our mapping is going to be AES, and then on the X, we care about age. So X is going to be the age column. So maybe our question is, what does the distribution of age look like in our data set, right? So if we just run this, remember, we don't really see anything. And the reason for that is because we don't have an actual geometry. And one of the geometries that ggplot gives us is geom underscore histogram. And so what this did was, given our blood data set, we wanted to plot against the x-axis a histogram. And you'll see that ggplot will give us a histogram. In here, you see that it says using bins 30 because there's too many bins. We can control the bin width. So it says by default, it's bins equal 30. So within his geom underscore histogram, we can say bin is equal to 10. Sorry, it's bins. And we can change the binning from our histogram that way as well. For more bivariate or columns that require figures that use multiple columns, we can say, let's say, for example, we want a scatter plot of their different what is this? So in our current data set, there is a column that represents the prostate volume in grams. There is another column that represents the pre-op prostate antigen value. And so we can plot those two values on a scatter plot because they might be related to our outcome of interest. And so we can say ggplot blood, and I can skip this data equals mapping equals stuff if I because it's in that set of order. So, but we still have to specify AES. We can say X is equal to this volume column. On the y-axis, it's going to be equal to the pre-op PSA. And then we can say plus geom underscore point to draw a scatter plot. And this is sort of the really nice thing with ggplot, because let's say, for example, you have another categorical variable. So, and you wanted each of these points colored by that categorical variable, you can simply say something like color is equal to another column. And for each value of that, each value in that column, it'll create a separate color for. Right now, we get a continuous bar graph here on the right-hand side. And that's because SGS is considered a continuous variable. It's 1, 2, 3, 4. It's a special score. It's a surgical score that they are given. If we wanted this score to be 1, 2, 3, 4 as like actual categorical numbers, like 1, 2, 3, 4 versus continuous numbers from 1, 2, 3, and 4, just like before where we said as dot numeric, we can say like, hey, turn this thing into an actual categorical variable. And so the way we do that in R calls categorical variables as factors. So we can say, hey, turn this thing into a factor variable, and you'll see in our figure, we actually get the separate discrete color scale 1, 2, 3, 4 on the side. And just the last thing I want to show off, which I talked about in the layering system, facets. I'll just show you facet wrap for now. What facet wrap allows us to do is, just like group by allows us to split our data into as many groups, do a calculation, and put it all back together again, a facet will do the same thing. So we have another category. We have another variable called rbc.age.group. And so now we can say, hey, take this scatter plot that we just made, and what I want you to do is create a separate scatter plot for each value of this facet variable that I specified. So I got a question about repeating something. Can you tell me what you want repeated?
Yes, since the part of the as dot factor SGS.
Mm-hmm. Oh, so SGS, if we look in our data set, in our blood data set right now, SGS is a special categorical score. So like they got a score of 1 if they weren't assigned to anything. They got a score of 3 if their surgical Gleason score was like a 7. They got a score of 4 if their surgical Gleason score was 8 to 10. So this is like a scoring system that's like a category 1, 2, 3, 4, not actual numbers 1, 2, 3, and 4. And so we want this number represented as separate groups. Those groups just so happen to be like numbers. So we can say turn that set of numbers into a category, because without as.factor, you see that one, like the color shading is really similar, and it's really hard to distinguish 1 to 4 because it's assuming it's on a continuous number line scale. But what we actually wanted to do is like, hey, we actually mean to have this on, they're separate things. They just so happen to be numbers. So turn them into categories. So this can be, you would want like male, female to be like more distinguishable colors because they're separate groups. But sometimes your data set will have male and female encoded 0, 1, or 1 and 2. And so this is something that you would end up doing. So your figure actually has like a discrete color palette versus a continuous color palette.
Yeah, true, thanks.
Okay. So that is the very quick intro to plotting that I want to go over because the last thing I want to cover is I'm going to try to teach you statistics in about like 20 minutes. So logistic regression. We talked about right before nominal, ordinal, binary variables. In our current data set, in our blood data set, we care about whether or not the person ended up having a cancer recurrence. And so that's a yes or no question. And in our data, that recurrence variable was 0 and 1, right? And so once you have an outcome of interest that's binary, typically the statistical test that you use is a logistic regression. And logistic regression is essentially just like linear regression, which is y equals mx plus b, where you draw a line through a set of points. Logistic regression is the same thing, except because our outcome variable is just 0 and just 1, we can't really draw a straight line because our data set, our outcome variable doesn't fit along a straight line. Like there's no straight line that can represent two binary variables. And so there's a transformation that essentially takes this straight line and makes it curvy and also in such a way where it's bounded between 0 and 1. Right? So it doesn't make sense to draw a straight line that goes from negative infinity to positive infinity and say like, oh, this is the model that fits my data, when your data only has possible values of 0 and 1. Like that is sort of like the definition of like you picked the wrong model for your data. So this transformation, this is all the math that you'll ever see in this class. It's called a logit function. And all you have to do when you're thinking about logistic regression is it's literally normal linear regression. We apply a logit function on top. When we go and interpret the values again, we have to undo bits and pieces of that logit function. And that's why when you look at articles that use linear regression, they don't report the actual values that come out of the model. They report something known as an odds ratio. And so when you see odds ratios, it's probably a good hint to yourself that you're looking at a study that is using linear regression, and that means that the variable or outcome of interest that they were looking at was a binary variable, like yes or no. And the only thing here that you have to know, because this plays into post-analysis data processing, is to get the odds ratio, you have to take you have to use the exponentiate function on all of your model outcomes to be able to interpret those values as odds ratios. So we will go over a very quick example using the current data set, our current blood data set, and then I'll show you how we can use exactly what we've already covered to look at our data set and interpret our results as proper odds ratios. So I'm going to say, make a new, whoops, I called it logistic without a number. I meant to call this 06. Okay, so what we're going to do is we're going to load up medical data again. and load up tidyverse. And what I'm going to do is restart my R kernel. So I have a clean slate. And then also reassign blood to blood underscore storage. So we have, run everything and then run blood storage. So I've reset everything back to before. From the previous portion that I just pasted into chat, we had this frequency table that we calculated, right? So this is the data in our outcome variable. There's already something that's problematic, and this goes more into like machine learning things that you would have to deal with. But you'll see that like our groups are really unbalanced, right? So if I was like a betting person and all I did was just bet everyone just didn't have a recurrence, my model will do pretty well because 262 out of the whole group is 0. So chances are I'm going to be correct, right? So this class imbalance is part of the reason why you want to do this preliminary exploratory stuff instead of just jumping straight into fitting a model, even if your data is prepared for it, because your model will essentially be very skewed to just guessing or saying 0 because most of your data points are 0. So that's something that you want to keep in mind. So how do we go about and fitting an actual logistic regression model? It uses the built-in R function called GLM for generalized linear regression. The way we specify the model is we say, so we have our blood data set. Let me give you names of blood instead. We have this recurrence variable. So that's the variable of interest. So that is our Y variable, or our, in social science, they're called our dependent variable. Sometimes you might hear this being called your response variable. So we have this little tilde. The thing to the left of the tilde is that dependent variable, response variable, and everything to the right is all of your independent variables, also known as your predictor variables. Depending on what field you're in, you might hear them being called different things. Sometimes they're also just called your X. So on the right-hand side, we have our X variables, or our predictor variables. Then we specify the data set that our model is going to be in. And to say that this is a logistic regression model, the part here that's most important is we have to say family is binomial. Data is blood. And so that's it. We fit our logistic regression model. That's model fitting is usually pretty simple, and it's everything else that takes a long time. I'm going to save this into a variable called mod1, just so we can look at it in a little bit more details without rerunning the variable all the time. So if I just look at mod1, you'll see that we have this coefficients table. And usually after you fit a model, you run it around this function called summary, and it gives you a whole bunch of things, but the most important thing here is that the coefficients portion you get for the variables that you specified, you get the actual estimate, and you get like a little p-value for your variable to the right-hand side. And you can see like this is not like a particularly good model because age doesn't actually predict whether or not you have recurrence. So maybe we want to put more variables into this model. So I'm going to copy all of that code again. I'm going to call this mod2. And how do we add more variables into our model? Well, to the right-hand side of that tilde, we literally put a plus sign and we add in all of the columns that we might want in our data set. So you're literally using a plus sign to add more variables into your model. And so now if we run fit that model and look at the summary, you might see that like this pre-op PSA seems pretty predictive of whether or not you're going to have recurrence after this blood transfusion. or after this surgery. So what we want to do is, given this data set or this model, we want to be able to interpret these results, right? So in regular linear regression, you might be able to say, for every 1 unit increase in age, this other thing will increase by this many units. That's typically how you interpret linear regression results. But because of that logit function I talked about, the way we interpret age here would be, for every 1 unit increase in age, the chances of having recurrence increases by the log odds of that number. And that phrase at the very end gets really weird. And it's also super hard. It's not intuitive. Like, what the heck is a log odds? So what we want to do is take the exponentiate all of these numbers, so then we can talk about them as odds ratios. And that sounds more like sort of more like the chance or the probability, and although that's technically not correct, but think of it as like, oh, the probability increases by this many times, is how we can sort of interpret that number, and that makes a little bit more sense. So how do we go about dealing? First thing we want to do is pull out this coefficient table. So how do we do that? There is a function that comes with tidyverse, or there is a library that comes with tidyverse called Broom. And you can think of, and there's a lot of puns in the R world. So Broom is like a broom that sweeps up and cleans up your models to make them tidy. So that's where that function comes in. Broom has a function. So we can say, given our mod, there's a function called tidy. And if we pass in any model object into tidy, what we get back is a nice little data frame of just the coefficients portion of our data set. And so now we have a data frame. So now you can either save this out to an Excel file if that's all you need to do. Like, I fit my model, here are my coefficients, someone else go deal with them. You can do that. But I also showed you the mutate function. So we can pipe this into the tidyverse mutate function, because what we want to be able to do is interpret these estimates as odds ratios. And so we can say odds, we'll create a new column called odds, and it's going to be the exponentiated value of this column called estimate. And so now we actually have proper odds values at the right-hand side. And I will paste into chat the only way you can like really interpret like these numbers. So the way we can interpret this, we interpret the odds on the right-hand side. So we can say, for every 1 unit increase in the pre-op PSA, the odds of earlier biochemical recurrence of prostate cancer, like so from going from 0 to 1, increases by 1.1 times, assuming everything else is equal. And so that's why when you read a lot of these medical journals and statistical papers, like the interpretation gets very rigid. And it's because that's really like the only technical way you can interpret that number. And we're sort of closing up on time, but you can, if you want, explore like the 3 models that I created for this example. The text is a little bit sparse. There isn't a lot of text in that example, but you can go through the code and you'll see what I'm trying to do in terms of like building the model, getting the coefficient table out, exponentiating the estimate column, so then I can interpret the number as a proper odds ratio. And that is the most important thing I want to get out of from this portion, is use logistic regression when your outcome of interest is binary, and when you fit the model, which is as far as everything that we've covered, like this actual fitting of the model, assuming your data set has a proper column that you can point to, is like one of the easier lines of code there. But remember, like, you have to have a proper column called age, or a proper column for recurrence or a proper column for p-val or pre-op PSA, right? Like, think about the tidy data examples. We could have very easily had, maybe there was a year column involved for time, and that was across every single column in our data set. We would have to do some kind of pivoting step before we get our data in a position where we can actually fit this model. So I just want to go through a few conclusion slides. If you have any questions about the model fitting, just let me know and we can talk about it. But I want to try to end somewhat earlier. So the question was like, what do I mean by fitting the model? So for the most part, fitting a model, at least in our current example, is drawing this line across our data points. There is a set of equations that need to get solved, which is like essentially what's going on when we say fit the model. When I say fit the model here is given age as a predictor and recurrence as the value I want to predict, give me some equation that I can use to plug in if I see a new data point of what the chances are that this person is going to have a recurrence value. The other question was, do I ever plot a curve in logistic regression? Short answer is no. And that is because this diagram here is, you might be able, you can plot this curve because this is really like, you usually don't see curves like this because just for the same reason when you see like large linear models, you don't really see like a scatter plot with a line through it. And that's because usually a lot of models is more complicated than y equals mx plus b. It's going to be y equals essentially b plus m1 x1 plus m2 x2 plus m3 x3, where each of those m's is a separate variable. So very rarely do you have a model that like this one variable predicts that other variable, and this is a great model. In which case you probably don't even need statistics if the thing is that like correlated and it's obvious. So that's typically why you don't see these types of lines being drawn, and it's because it's impossible to draw like a 10-dimensional figure. Like, how do you represent 10 dimensions? And that's a whole other field of like dimension reduction. Just so like, how do you take 10 dimensions, boil it down to 2 dimensions, and still accurately represent what is going on in 10 dimensions? Like, things are gonna get lost. So that's why you typically don't see those figures being drawn. You'll see other plots that like are diagnostic plots. You might see those being drawn, but that's different from like, here's the line that like fits through all my data. You usually don't see that one. So as far as fitting the model is concerned, this little tilde notation, also known as the formula notation, is the relationship or the inputs or what you think will predict this particular outcome. And so that is the model that we are specifying. When I say fit the model, I mean, hey, we're gonna pick one of these statistical methods and try to draw a line, a theoretical line through all of these points as best as possible. So you might have different models that fit different use cases, and each of those models have like a specific like assumptions that are built in. Like logistic regression means that your outcome is binary. If we try to fit it against something that's not binary, chances are R is going to tell you something is wrong. Okay. So keep asking questions and I'll just go through the last set of conclusion slides. Hopefully this was a not so terrible introduction to R. Hopefully, at the very least, you're able to load up a data set and look at it, maybe save out something, like do a small pivot step, save it out to Excel, continue on with the rest of your data analysis pipeline. Hopefully, within the last 2 days, you saw something that is relevant to your work. And if that's all, if that one step is all you need or all you can do from R, I will call that a win. Even if it's you process your data in Excel and you're using R to run that one little GLM line to do a model fit, to do a statistical test, I would also call that a win. So additional resources. This is in the slide deck. If you want, you can totally take a screenshot of this now. And I will put this in the follow-up email within the next week. So there is an R4DS book. It goes into more detail. It is more general. It doesn't have examples that are medically related, but it is written by the folks at RStudio, and it's a very good introductory R book as well. The R4DS book has a online community. It is a Slack group, and you can join the Slack group at r4ds.io/join. What's really nice about there is they are actually right now, they have, I'm part of it, so you can always find me there if you need to ask me a question. They run many book clubs that happen, so I can probably show you what's going on in one of mine. So right now they're reading another book called Tidy Modeling in R, and that's the one I participate in every Monday. They have different cohorts. They have other book clubs that are being held throughout the year. They also have office hours, so you can literally like call in on Zoom and ask somebody who's hosting office hours. Online, you'll see a resource called Tidy Tuesday. And so this is every Tuesday of every week, a new data set gets released out into the wild, and then folks on Twitter spend a week like drawing a plot with it. And so you can follow that hashtag on Twitter for inspiration on what you can do in R. David Robinson also, I have to check if he still does this. He streams an hour of his Tidy Tuesday work on YouTube. So if you just want to watch somebody like someone who's really proficient in this tool set just go through all of the tips and tricks of like what can be done, that is something that you can watch, and maybe you'll learn a couple of new functions from libraries that we've talked about these couple of days, or learn about new libraries. That's a really good resource as well. If you identify as a lady, you can join the R Ladies group at rladies.org. They have a totally separate Slack channel. So if you want to ask questions, you can join the R Ladies group, and they can help you with R-related problems or questions. If you are more reluctant to just ask your question out into the wild, so that is a more welcoming community if you identify as a lady. For the people in medicine, there is the R Medicine Twitter group. They also have their own Slack group that you can join, and these are medical doctors, clinicians that work in R, and they do kind of cool things in R. They host a conference every year, and proposals are gonna come up in about 2 weeks for the R Medicine conference that is being held in either August or September. I believe those are the dates. And if you want more free R resources, there's literally a book that is being catered around all of the free R resources that you can find online called Big Book of R. Data services is something that's VT related. That's also something VT related. The carpentries, Nathaniel Porter is the contact at VT. There are many contacts at the UVA side that I'm sure Marika can point you to. But these are also other free resources that are more domain specific, and you can find them in R as well. And the last thing I want to go over is, please, if you can, take my post-workshop survey. That would help my dissertation a lot. I understand that my Zoom kept crashing. If that has affected your ability to learn, please do let me know, because that will also, it's good to have those data points to say like, yeah, this was actually really disruptive, or like it broke in such a way where it wasn't disruptive. I have no idea. So do give in feedback. One of the questions that I find really important in there is if you find something that you wanted to learn, but then also tell me what you would take out. That is always the hardest problem of managing content. So with that, that's all I have to say. We're at time. So Marika, if there's anything you want to say to conclude,
Yeah,
I'll be around.
I'll just share a UVA specific resource. The easy, quick way to say it is just get in touch with me or Andrea. You can get in touch with us through our website, data.hsl.virginia.edu, or just our emails, marika@virginia.edu or andrea@virginia.edu, and we can always send you to the right spot or the right resource.